In this video lecture, we will look at the parallel homogeneous learning methods known as bagging and random forests. Both of these methods typically learn ensembles of decision trees. Let's get started with bagging to see how this works. So bagging seeks to reduce model variance by training a large number of decision trees on different samples from the original dataset. It seeks to leverage the statistical property that for independent random variables, the sampling distribution of the mean is 1 over t times the variance across all models. Here, t is the number of trained models. This means that averaging appreciably reduces the variance of the model. However, if we only have one training dataset, where do all these independent samples come from? It turns out that we can generate a number of new datasets from our one sample through a process known as bootstrapping. Here, the idea is that given our original dataset X, which has n examples or rows in our case, we can create t new copies by sampling with replacement. So here, by replacement, I mean imagine that we were picking out examples from a hat, and we did so one at a time, always replacing the ID of each example after each turn, such that the same one could get selected multiple times. This means that, even though the total number of rows of each bootstrap sample, xm, will be the same as for x, the composition of each will be different, as some examples will get repeated and some will not get sampled at all. In what follows, we will show that for large enough samples, bootstrap sampling will closely approximate any sampling distribution estimated from the full population. To see how this works, let's go through an exercise of creating bootstrapped examples from a small toy dataset. Go to Notebook 7, Ensemble Learning Exercise 1. I'd like you to edit the function bootstrap sample in order to generate bootstrap samples from a data matrix dataset by editing this line 10. Specifically, what we're expecting is that it returns this matrix samples which has the same number of rows as dataset, but a different composition. So specifically, we're asking you to use the function numpy random choice. The link to the documentation is here. With replacement set to true, in order to return a list of indices corresponding to the rows of the data matrix, which will be used to slice the dataset, as shown in line 12. Pause the video now and give this a go, testing it on the toy dataset in the cell below. An example of what we're expecting from this indices list is shown here, such that we can sample certain rows multiple times and other rows not at all. So I've switched now to the notebook to demonstrate the answer to that task. So what we were specifically asking you to do was input the function numpy random choice to return a bootstrapped sample from the matrix dataset. Numpy random choice expects as its argument either an integer or a 1D array. So we can't use it to fully randomly sample from the dataset directly, but we can use it to create a bootstrapped sample of row indices, as I showed on the previous slide. We need to input numpy random choice with range equal to n sample, as this equates to the number of rows in the dataset, set here. And we want it to return the array indices also with length n sample, because we want the number of rows of our bootstrapped matrix samples to be the same as the original dataset. And finally, to enforce sampling with replacement, we must enter replace equals true. Note, this is one approach, so if you instead chose to pass an array of row indices to random choice, instead of just an integer, that's also fine, but not necessary. The important thing is that you've got a function that works. Now, just for ease of interpretation, I'm going to print out indices so we can check whether they're correct. Where don't forget to go back and remove it afterwards before you go on to the next section. So let's run this cell and then test the function on the small toy dataset below with 10 rows. So hopefully you should see that the indices array, as we showed on the slide, samples some of these rows repeatedly and others not at all. And so with respect to our original dataset, our bootstrapped dataset contains some of these rows multiple times and others not at all. So this is the way that we get a different dataset each time we bootstrap. Then, once you've got that working, you can run the next code cell in the notebook to see how bootstrapping can be used to approximate sampling distributions that otherwise would need to be estimated from the full population. So, let's imagine that we had a real-world large random population, which for this we're going to create a long array with 100,000 integers in the range 0 to 20. And we're going to call it data population. The idea is that if this was a real-world population, for example, we wanted to obtain brain scans from the whole human population, we simply wouldn't have the resources to do that. So in reality, what we would do is take a sample as big as we can manage. So let's call that data sample. So because this is a 1D array, we're able to use NumPy random choice on it directly. Once we've got our data sample, then what we need to do is compare the performance of estimating a sample mean by repeatedly taking bootstrapped samples from data sample relative to what we would get if we had the resources to repeatedly take large samples from the full population. So here I show the next cell in the notebook highlighting the key points. So at the top here, this is where we create or simulate our true population, and then we print out the mean. Now what we want to do is compare generating a sample distribution of the mean by repeatedly taking samples from the full population with what we would get if we sample our population only once, but then simulate new data sets through bootstrapping. So here we have a loop running this process for different sample sizes of our data sample. So imagine that data sample is the experimental data that we're able to collect. So now we have a bootstrapping loop where we estimate the mean from a bootstrapped sample from our collected data sample. And we save all of this in a list. And then we compare this against repeatedly taking sometimes large samples from our original data population. And we store those means here. And we do this 100 times. Then we compare the statistics, so the distribution of the sample means from the bootstrap sample, and what we would achieve if we could repeatedly collect increasingly large samples from the full population and run repeat experiments on all of those, which we know in the real world is rarely possible. And what we want to see is that the mean distribution returned from repeat bootstrap sampling from a single data sample will be comparable to the ground truth sample distribution of the mean estimated from the full population. So plotting these results for each of the different sample sizes, we can see that this is the case for large enough numbers of samples, where what we're looking for is that the distribution is centered on the true mean, which is 9.51. So in the first example, we show the result when the sample size is 1. In this case, it's not surprising we do a bad job, because data sample just has one row, so it doesn't matter how many times we bootstrap from it, it will always be the same. In this case, it's 3, which is far from the population mean. However, as sample size increases, particularly once we get to 1,000 samples or more, bootstrapping gives a good approximation of the true sampling distribution, and this increases to achieve almost perfect overlap once we get to a sample size of 1/10 of the size of the full population. You can also see that the variance of these distributions also decreases as we increase sample size. Therefore, bagging, shorthand for bootstrap aggregating, uses this property, taking repeated bootstrap samples from the training data and independently training in parallel separate weak learners on each. So here we assume that these weak learners are trees, although in principle they could actually be anything. Once trained, test examples are then passed down all of these trees to get several predictions for each test example. The scores are then aggregated using either majority voting for classification, which we saw an example of in the first video, or for regression, we perform averaging to return one prediction for each test example. So this leads to much improved performance, as you will see in Tuesday's tutorial. We're going to test on the scikit-learn make-moons dataset, a simulated dataset which is non-linearly separable. So here we have two classes, red and blue, where the distribution of the data points in the class are shaped as crescents with intersection, which makes them difficult to separate. And we've separated out these datasets into training examples, which are closed circles, and test examples, which are shown by crosses. So when we train a decision tree on this, we do an okay job achieving accuracy of 8.75, where hopefully you can see, however, that these blue examples are mislabeled because they should belong to the med class. On the other hand, the bagged example gets all of these examples correct, with just one error for this isolated blue point here. So we'll do this with scikit-learn. So when it comes to the scikit-learn implementation, there are a couple of arguments worth pointing out. The first is that whilst decision trees are the default base learner for ensembling with bagging, actually you can choose any other predictive model. Secondly is this out-of-bag score, which allows evaluation of the likely generalization potential of your model. So specifically, out-of-bag error leverages the examples that get left out of every bootstrap dataset. Remember, some examples will get included multiple times and some will always get left out, where, for large enough datasets, it can be shown that this is approximately 37% of the total. So we can use these left out examples to validate performance of the model during training, where specifically for each one of our training examples we need to find all bootstrapped examples which don't include it, and then estimate the predictions on all the models trained on these datasets. So here, for each training example, we are only returning predictions for base learners for which it was left out and not used during training. Once we've got these predictions, then we need to combine them using averaging or majority voting to get an out-of-bag prediction for each individual training example for all of the models that it wasn't used to train. These then need to be combined to calculate a model score over all out-of-bag examples and get an overall out-of-bag score from the model. Finally, for classification, as this returns accuracy, the proportion of correct samples, to get the error across all samples, you must subtract this from 1. So plotting this, you will hopefully see that by increasing the number of base learners, trees in this example, which are trained in our ensemble, we continue to reduce the error up to a saturation point. So hopefully you can see that in this way out-of-bag error can be used for parameter optimization. There's an example of how to do this in section 2.1.6 of your notebook. So specifically here, we purposefully use scikit-learn's make classification function in order to simulate a two-class problem where, importantly, only 15 out of 25 features are actually useful and the rest are noise. So this allows us to simulate a noisy dataset which would be prime for overfitting. Then we create a loop where we build bagged examples for different numbers of trees, where the loop variable nTrees is passed to the model using the argument nEstimators, and we turn out-of-bag score tracking to true. Then we fit the model and estimate the error as 1 minus the out-of-bag score, and this returns the plot that you saw on the previous slide. So in conclusion, bagging seeks to create uncorrelated predictions through training on multiple datasets generated by bootstrap sampling from the original dataset. It's very useful for datasets with a lot of noise, where different subsets of data can really skew the predictions. However, it's important to be aware that given the opposite case where predictions are actually stable across trees, then bagging may even lead to a degradation of the result. So this then brings us on to random forests, which seeks to increase the robustness of the models to feature noise by increasing the variability of the dataset that each base learner is trained on. So specifically, random forests work by limiting the choice of features available at each node in each tree to a subset. This has the result of further decorrelating base learners of the ensemble, therefore further decreasing variance and increasing stability against feature noise and thus the chance of overfitting. So the building of decision forests can be summarised as follows. First, for each tree, create a bootstrapped sample from the full training dataset. So this is exactly the same as what you would do with bagging. Then you train the trees on these samples, splitting at each node until a termination criterion is met, such as, for example, max depth is exceeded or the number of training examples in each leaf is less than the minimum allowed. Again, this is completely consistent with bagging. The difference between forest and bagging is that while doing so, you restrict the available features that each decision stump can choose from. So this is done by just sampling random subsets of columns from the dataset and instead presenting these to the splitting function. In this way, each node of the tree sees slightly different subsets of features. Thus, the axis-aligned stump is trained maybe without seeing the absolute optimal feature for that level, but it means that the tree needs to find different ways to solve the same classification problem, which builds in redundancies and increases robustness against noise in the feature space. Once trained, as before, each leaf node is assigned a prediction, and then the whole process is repeated for each new tree in the ensemble. Subsequently then, at test time, each example is passed down all trees, and each test example is given a prediction for each tree model. Finally, an aggregated score is obtained across all trees in the exact same way as for bagging. Indeed, the whole test and train process is exactly the same as for bagged ensembles of trees, with the only exception being the random selection of feature subsets during training. So again, in Tuesday's tutorial, we will go through the process of training random forests using scikit-learn, noting the use of the max features argument, which will control the proportion of samples considered at each node in the tree. We will also show how ensemble methods such as random forests return a really useful attribute known as feature importances, which can be used for feature selection, which will be described in week 8. So in optimising random forests, these are the parameters that I would consider. First, the numbers of features per node. Note this is a trade-off between bias and variance, because if you severely restrict the number of features at each node, then you may harm the accuracy of the model, especially if there are a very limited number of features that are useful for the prediction. Typically, the default offered by scikit-learn is to select from a number of features equal to square root of m, where m is the total. Other options include sampling log to the base 2 of m, or some other predefined fraction of m, or indeed all features. However, in that case, you're just performing bagging. The other things to try would be to vary the number of trees, where you saw from the out of bag example that this improves performance up to a limit. So essentially you have a performance runtime trade-off. Finally, it's important to consider setting a max depth or min number of samples per leaf to discourage overfitting. Note, min samples per leaf will indirectly control for tree depth, but in a more adaptable way, making it potentially a more powerful choice. Finally, a really powerful aspect of all these ensemble methods that we're looking at is the fact that they balance performance and interpretability really well. So each of these homogeneous methods that we're discussing today combine very simple and clearly interpretable decision stumps, but in slightly different ways. But these decision stumps are each making very simple decisions based on just thresholding individual features. And this aspect of training is really important, as it allows for users to return the most important features for any prediction, simply by checking how often each feature is chosen by each decision stump in the ensemble. These importance rankings can be really useful, for example, for use as feature selectors prior to use in another model, or for a second learning stage, as you will learn about next week. But also because they make it easy to build explainable models. as for example in medical imaging, one could subsequently highlight those features as potential biomarkers of disease progression, or go on to construct mechanistic models of how those specific image features relate to biological processes or the progression of disease. So in summary, bagging and random forests are parallel learning ensembles based on common principles. While bagging in principle can be applied to any learning model, it was originally designed for trees, and random forests was an extension of that. The idea is that many different weak learners are trained independently in parallel and then are aggregated either using majority voting or averaging, where the goal is to make the base learners as uncorrelated as possible by adding randomization into the training process. Both approaches do this through bootstrap sampling of the datasets. Random forest also trains decision stumps on random subsets of the features. Together, these work to decorrelate predictions and reduce model variance by averaging away the impact of isolated errors. The likely generalization performance of bagging and random forest models may then be inferred through plotting the outer bag error, which makes use of training examples left out from training each base learner as the result of bootstrapping, and these left out examples work to validate the likely performance on unseen data. Finally, a really powerful feature of all homogeneous ensembles discussed today is that they return feature importances. This tells us which features were most important for building a model, and so is useful for feature selection and model interpretation. So that's it for the section on bagging in forests. Although with a lot of material to take in, make sure you've gone through the bootstrapping example in the notebook and then answer the very quick Keats quiz to test your understanding before you go on to the next video on boosting.